We've discussed addition and multiplication. Now let's talk about division. So again, let me start out with the standard grade school division algorithm that you've seen, or the steps involved in that. Let's start with some number 795, and I'm trying to divide this by the number 31, let's say. Okay, the way we do it is we first take the most significant bit here, and then we see if 31 is less than 7. Well, in this case, 31 is greater than 7, so that's not enough. Let's look at the next bit. So each time I feel the need to look at one more bit, I essentially have to put a 0 into my quotient, which is the result of the division. Okay, so now I'm going to look at 79. 31 is now less than 79. In fact, 31 times 2 is the largest number that is less than 79. So that gives me a 62 over here. Okay, so now I have to take 62 away from 79, so I do a minus. That gives me a 17 over here. Okay, and then I look at the next bit as well. So that gives me a 5 down here. And then now I do 31 times 5, which is the largest number less than 175. That gives me 155 over here. That gives me a remainder of 20. Right, so 795 divided by 31 gives me a quotient of 25 and a remainder of 20. Right, so that was my grade school algorithm for doing division. And let's do exactly the same thing over here. And again, I've carefully chosen the numbers so that the exact same steps would apply to these numbers, whether you treat them as decimal numbers or as binary numbers. Okay, so if I'm going to try and take this number 130, and I'm going to try and divide this larger number. So first, I'm going to take the most significant bit over here, compare 1000 to that number. Obviously, this number is larger, so that's not good enough. So I'm going to put in a 0 into my quotient. Then I look at the next bit. I can compare the two. Again, this number is larger, so I put in a 0 over here. Right? So there's nothing wrong in putting zeros at the start. Really doesn't change the result. Right? We usually ignore that when we are doing grade school division, right? But let's just kind of go through the steps formally. Then let's look at the next step over here. Compare the two. Again, this one is greater, so put in a 0. Then I look at the next bit. Now finally this number is less. Okay, so I'm going to put in a 1 over here because I'm going to put 1000 times 1 over here. Okay, and now I'm going to subtract the 2. I get a 1 that is left over. Okay, now time to look at the next bit. Take the 0 and put it down here. Compare this number to this number over here. This one is greater, so I have to plug in another 0 into my quotient. Okay, now these zeros are relevant, right? I mean, these are not zeros that you ignore, like the leading zeros up here. Then I look at the next bit, put down a 101, compare the two. This one is still greater, so I put in one more 0 down here. Time to look at one more bit, which is this next 0 over here. So I look at 1010, compare the two. Now finally this number is greater. So 1000 times 1 is 1000, gets placed down here. Subtract the 2, I get 10 left over. Okay, and now I've run out of bits over here. So that's my final quotient, 1001, and 10 is my remainder. Okay, so you'll see that these steps can be very clearly formalized, right? At every single step, I'm comparing the divisor to what is left over in the dividend, right? So this is referred to as the dividend. And every time I do the subtraction, the result gets placed back in the dividend. Okay, so at every single step, I'm looking at one more bit of the dividend and comparing the divisor to that. So in some sense, what is happening is I have this dividend register over here. And then I have a divisor register over here. Okay, and that large number, let's say 1000, and then this is this number over here. Essentially, this guy keeps moving towards the right, and I check to see which of the two numbers is greater. Okay, and while the divisor is greater, I basically keep moving it to the right, and I keep shifting a 0 into the quotient. Finally, when the register on the top is larger, right? So once this has shifted 3 places to the right, you get something like this. And then a bunch of zeros, let's say. Now finally the divisor is smaller, so now I shift a 1 into the quotient, I do the subtraction, and I place the result of that subtraction back into the dividend. And then the divisor then continues its trek towards the right, right? It keeps getting shifted to the right. I keep doing the same steps. And so this is how you formalize the algorithm. Okay, so maybe this will be made more clear as we go through more examples, right? So let's do this one more time with these steps that I just described, right? So as I said, there is the dividend register up here, okay, which is this large number here and a bunch of zeros before it. Okay, so in fact, what I'm trying to do here is take a 32-bit dividend and a 32-bit divisor. Okay, so I put both in 64-bit registers. Okay, so this is initially my divisor, 32 bits, and then I put a bunch of zeros here. I put my 32-bit dividend here and a bunch of zeros before that. Okay, so this is my dividend with a bunch of zeros, and then this is my divisor with a bunch of trailing zeros. Okay, and so that divisor is going to keep moving to the right. Okay, so initially I compare the two. This one is smaller, so I put a 0 into my quotient, and then I keep moving it to the right. I'm kind of ignoring those steps, but essentially a bunch of zeros get shifted into my quotient. And then finally, my divisor has come under the dividend so that this number is now greater. When that happens, I shift a 1 into my quotient, I subtract the 2, and the result is now this, which gets placed into the dividend register. Okay, and now again the divisor continues its trek towards the right, right? So we had 6 zeros here, and now it's moved to the right, so we have 5 zeros. And again, if the number on top is smaller, then I shift a 0 into the quotient, right? So I shift a bunch of zeros. It finally comes down over here, where after a few shifts, you realize that again the dividend register is larger. That means I shift a 1 into my quotient, do the subtraction, that gives me 1 0 left behind in my dividend register, which is my remainder. Okay, so hopefully this example again shows you what's happening. This is clearly complex, so let's do yet one more example, and you'll see the various steps involved. So let me just fill out this table, right? So this is a different example where I'm taking the decimal number 7, dividing it by the decimal number 2, right? The corresponding binary numbers are shown here. To make things simple, instead of doing 32-bit math, I'm taking a 4-bit value and dividing it by another 4-bit value. Okay, so I'm going to start with 8-bit registers. So my divisor is this value here, and then it's padded with zeros at the end. The dividend is placed in the dividend or the remainder register. It gets placed into the least significant bits, right? So 0, 1, 1, 1 is placed in the least significant bits, and there's a bunch of leading zeros up here. Okay, so the goal is always to compare the divisor and the remainder. The way you compare these two is subtracting the divisor from the remainder, right? So the very first step I do is remainder minus divisor. I check to see if this value is greater than 0 or less than 0. Okay, so once I do that subtraction, the result gets placed here, right? So basically 4 zeros followed by 0, 1, 1, 1. This was my remainder register or my dividend register. My divisor is 0, 0, 1, 0 followed by 4 zeros. If I do the subtraction, the result I get is what I'm showing you there, 1, 1, 1, 0, 0, 1, 1, 1. Okay, by looking at the most significant bit, I know that this is a negative number. Okay, so if this result is less than 0, then this is a division that should never have happened, right? I should really be shifting a 0 into the quotient. So the quotient basically remains unchanged because I shifted a 0 into it. But then I need to get the remainder register back to its original state. The way I do it is by just adding the divisor back, right? So what I've done in the previous step was to subtract the divisor out of that register. Now I'm just going to add it back so that things go back to the way they used to be, right? So the remainder register goes back to being the same value as before. Okay, then to get ready for the next step, I take my divisor and I shift it to the right. Okay, so this 1 basically moves down to this next bit. All right, now let's repeat the same process. It's the same steps as before. I take this value and subtract it from this remainder register. The result gives me this value here. Most significant bit is the 1. That means the remainder is less than 0. So just add the divisor back. The remainder register goes back to its original state, which is shown here. I need to shift a 0 into my quotient, so that remains unchanged. And then the divisor moves one place to the right. So now move on to iteration 3. Again, we'll do exactly the same steps as before. Turns out that the divisor is still larger than the remainder register. So I shift a 0 back into the quotient. That remains unchanged. The divisor shifts one more place to the right. Okay, and the remainder is also going to be unchanged. Now finally we have something interesting happening here, right? So now when I do remainder minus divisor, I get this result, where the most significant bit is a 0. Okay, so that means this was a successful subtraction. Time to shift a 1 into the quotient, and that's it, right? And then I just basically move on to the next step. Before I do that, I shift my divisor again one place to the right. And now again I subtract this from the remainder register. Again, the result turns out to be a positive number. So I shift one more 1 into the quotient. And what I get left with is a remainder of 1 and a quotient of 1, 1, right? So basically dividing 7 by 2 should give me the result 3 as the quotient, which is indeed the case, and a remainder of 1.